Okay, so that takes us through the fluorescence. Next thing, we're going to go through the fluorescence microscope, and we're going to focus mostly on an epifluorescence or a wide field microscope. On the left here, this is an example image, and then a confocal microscope on the right-hand side, which you can see is giving us a much sharper image than the wide field system. And what I thought would be useful for you to understand how these microscopes work is if we go through the structure of the microscope. So this is taken from a very good microscopy education webpage, but it's a very, very complex overview of what happens within your microscopes. But yeah, probably good for you guys to understand that there's a lot going on behind that eyepiece that you're looking in. I like to condense it down for the sake of this talk into a few kind of key parameters. So that is going to be the light source or the illumination, how we're illuminating our sample. Something called the excitation filter, which is selecting the wavelengths that we want to excite with. We're going to bounce off this thing called the dichroic mirror, go down through the objective to our sample. That's going to excite the fluorophores within our sample, and then we're collecting the fluorescence that's being emitted from that sample back up through the objective, through the dichroic mirror, through an emission filter, and then up to the eyepiece or to a camera. So we're going to focus on the illumination, the excitation filters, the objective, the emission filters, and the digital camera. Okay, so in terms of illumination for a wide field microscope, there are multiple ways we can do this. Historically, these have been kind of bulb related, so very intense, producing very intense white light. More and more nowadays, the systems are converting onto light emitting diodes. So in terms of bulbs, so as I say, we're producing intense white light that's producing at certain peaks across the visible light spectrum, so from 300 out to 800. And these bulbs have been selected to really line up with some of the common fluorophores that get used in scientific experiments. The nice thing about light emitting diodes is that they're only going to emit across a very, very narrow range. So they're very, very different to the kind of white light bulb source. So very specific, longer lasting. I mentioned the excitation filter. So that's the next thing that's going to hit, the light's going to hit after it comes out of the light source. So this is normally what we call a bandpass filter, which means it's only going to let the light in this very narrow band transmit through. So you can see the white light coming out of our source, it hits our excitation filter, and that's filtering out everything apart from the green light that we want to excite our fluorophore with. These excitation filters normally sit within a filter cube. So this is the light coming in. That's the excitation filter, which is blocking out most of the white light and selecting just the wavelengths that we want. It hits this dichroic or dichromatic beam splitter mirror. This is a specially tuned mirror which will reflect that light coming through from the excitation filter down through the objective to the sample. And then because of the Stokes shift in fluorescence, remember we're increasing the wavelength of light that we're collecting coming back through the objective. This mirror is specially tuned to allow that longer wavelength to travel through. And then again, we have an emission filter here, which will select the light that's going up to the eyepiece or to the detector. Okay, jumped ahead a little bit, but we're bouncing the light through the emission filter, down through the beam splitter or the dichroic, and we're going down to the objective. So this, I would argue, is the most important part of your microscope. Very often it's also one of the most expensive parts, but it's really important that you guys understand all of the information that's available written on those objectives. So let's get through some of these. First thing is our aberration correction. So in this, our flat field correction is a plan. And that basically means how even is the light going to be across the entire field of view. In this case, our aberration correction here is apo. That's our chromatic aberration. That's essentially how well aligned the different wavelengths will be. So is my green signal going to be at the same focus point as my red signal? The next thing to look at is the magnification. So obviously, the higher the magnification, the higher detail you'll have in your image. The number that comes after that is what's known as the numerical aperture. That gives you a readout of the resolution of that objective. The next one after that is the immersion medium. So if it's an oil, a water, a glycerol lens, it will say there. If it doesn't say anything, then it will tend to be an air lens. Air lenses also tend to have an NA below 1. So that's a bit of a giveaway if you're ever concerned. If your objective has a 0.7 NA, then it's almost likely to be a air lens. Next thing down here that's really important is our cover slip thickness. So 0.17 corresponds to 170 microns. That's a number 1.5 cover slip. So you will find that most of the lenses within a modern day facility will be expecting a cover slip thickness of 170 microns, or this number 1.5 cover slip. If you go back to your lab after this lecture and you see that there are number 1 cover slips that your lab are using, then you will be affecting the quality of your imaging, especially if you're doing it in the Z direction. Please make sure that you have number 1.5 cover slips available. The last thing to really pay attention to is the working distance. So here, because we're high magnification, we've got a very, very short working distance. So this is only 210 microns past the cover slip that we can actually image our samples. So very often we'll have people bring samples in microtiter plates that have a 2 millimeter thick base, and they wonder why they can't focus, and that's because they don't have the working distance on that lens to be able to actually image that sample. So the objective is really, really important. That means you have to take very, very good care of it. So for any air lenses, we would ask that you avoid contact with immersion oils. Certainly if it's any of our instruments, if you come across an air lens that it's difficult to focus on, it's probably that someone's contaminated it with oil. Please let us know as soon as possible so that we can come and clean that lens for you. It's a bit more involved than cleaning a normal oil immersion lens. In terms of cleaning oil immersion lenses, then please use properly designed lens tissue for doing this. If you're using Kim wipes or tissues, then you risk damaging the front part of the lens. So we normally suggest that you place a strip of lens on the glass part of the objective and just leave it there to absorb in the majority of the immersion oil. Do that 2-3 times until you've picked up most of the immersion oil. If you have to, then gently slide the lens tissue from one side to the other without applying any real pressure onto the objective. We then ask people to repeat this with the lens tissue soaked in solvent. And then at the very end, just wipe down the metal part of the objective to clean off any excess oil or ethanol that still remains. Again, if you're unsure how you should be cleaning an objective lens, then speak to the person who's in charge of that microscope in terms of how you should approach that. Okay, so our light has gone down through the objective. It's excited our fluorophores within our sample. We're then collecting the light that's being emitted from those fluorophores back up through the objective. We've gone up to the filter cube through that dichroic mirror. So you remember the Stokes shift now means that that light can transmit through. The next thing we're hitting is the emission filter. And you will find that they come in lots of different flavors. And you'll find that the name changes depending on what the type is. So there are short pass filters, long pass filters, and band pass filters. So band pass we've already discussed. It's a narrow band of specific wavelengths that it's going to let through. Long pass in this case here, we've got a long pass 520, so that's going to let anything longer than 520 nanometers transmit through. Short pass does the opposite, so if we had a short pass 520, it would be anything shorter than 520 nanometers. So again, check your instrument in terms of what emission filters you have in place, and just make sure that that's suitable for the experiment that you're trying to perform. Here we've got an example of what we call a dual bandpass filter. So this filter allows light through in both the green and the red channels. This can help with the speed of acquisition. So when combined with a diode excitation source, you can have one filter in place, excite your green channel here, collect that, and then turn the excitation for the green channel off, turn the excitation for the red channel on, and collect the red filter, all without having to move this filter block out of the light path. So again, if you're doing camera-based work, that can really help speed up your acquisitions. Finally, the light is going through your excitation filter and then up to either an eyepiece for you to visualize your sample, or normally across to a digital camera. So when it comes to fluorescence, your digital camera should normally be a monochrome camera. And there are lots and lots of different types of cameras available. And again, it's a 1-hour lecture in itself, going through all the different types and possibilities. So we have charge coupled devices, electron multiplying charge coupled devices, which are normally used for kind of low signal, scientific CMOS, which can be very, very fast. And again, there are multiple different types of these cameras available. So these back illuminated scientific CMOS cameras can give very, very clean signal. And the development of cameras are getting so good now that we're getting up to, for a couple of cameras on the market, there's scientific CMOS cameras with 95% quantum efficiency. So we can really detect as much of the fluorescence that's coming out as possible. So some of the considerations you'd look at in terms of setting up your camera is, as I mentioned, the quantum efficiency. So how efficient is it at converting signal, so light into electronic signal? The pixel dimensions of the camera and what that means in terms of your sampling of the image. And again, we'll come to that, I think probably more likely in Thursday's seminar. Whether it's monochrome versus color. So as I say, most fluorescence cameras should be monochrome, although you can image using a color camera if you really want to. It's just not as efficient as a monochrome camera. And then finally, the bit depth, which is the number of distinct units that you're separating your light out to. So like an 8-bit image is 256 grayscale values. Is that enough for you to really quantify what you're looking at? And again, we'll cover bit depth in Thursday's lecture. Okay, so that was a walk through a wide field or epifluorescence system. And these are ones that very often sit at a kind of lab or departmental level. They certainly do here at the University of Melbourne. And they're very good as a starting base for optimizing experiments and things, but very often if you want to get publication quality imaging, then you want to use something more like a confocal microscope. These are a little bit more technically complicated and therefore expensive, and that's why they tend to sit mostly in facilities like ours. So on the left-hand side here, we've got our wide field system. So in this case, we're illuminating the full field of view and we're collecting light. For fluorescence, on a wide field system, your best imaging is done about in the first kind of 20 microns past the cover slip. On a confocal microscope, what we're trying to do is to look at a very, very thin optical section within our samples. So we get a much better signal to noise, and better image quality as a result. Okay, so similarly to the wide field system that we walked through, we're going to walk through the structure of a confocal microscope. And again, just very high level overview of what the different parameters are. So again, we're looking at the illumination source. In this case, it's going to be lasers. We've got excitation filters, so I'm not going to cover that again. We have a scanner, which isn't really shown on here. We have a pinhole, which is the thing which is giving us that thin optical section that's sitting in front of a detector. And then finally, we're going to talk a little bit about the fact that we're generating an image here through this confocal detector. So very similar optically set up, but obviously with different components along the way. Okay, so why laser illumination? So the nice thing here is it can be a single wavelength, which means we don't necessarily need the excitation filters on the system. It can be a narrow parallel beam, so what we call collimated, and it can also be very, very bright. So this is just, I guess, the same images we showed for the wide field, just to show you that we have essentially a single wavelength here, which we're exciting our sample with. Again, like the fluorophores that we have across the visible light spectra, we have access to lasers as well across those visible light spectra. And handily, a lot of these are set up to match with kind of the common fluorophores that we're using. So very often you'll be using an argon laser, although again, this is switching mostly to diodes. This matches nicely with the excitation wavelength for something like a GFP molecule. Okay, unlike on a wide field system where I mentioned we're illuminating the whole sample and capturing the data out onto a camera, which is a one-shot thing, on a confocal, what we're doing is scanning that laser beam across our sample and building up an image over time as we scan across. So the scanning is controlled by two mirrors, one which controls the X position and one which controls the Y position across the sample. And the excitation light goes through these mirrors down to the sample, but then also comes back the same way to go to the detector. And that's what we call D-scanning. The detector, as I said, for confocal isn't a camera-based, so it's what we call a point. Sorry, I've skipped ahead a second. Yeah, so our detector is a point detector in this case. So what we're doing is using a pinhole which sits in front of the detector. So this little thing here is our pinhole. And it works, if anyone's into photography, it works very similar to the iris on a camera. You can control the depth of field, basically. And what we want to do is to set that pinhole to a position where only light from our current focal plane of interest can actually get through to the detector. So the light emanating from this dotted line here crosses over through the pinhole and gets to our detector. Whereas if the light from out of our focus hits the pinhole and can't get through, and light from below the focus hits the pinhole and can't get through. And that's how we're really cleaning up that optical section and making a really sharp focal point on the system. Okay, as I mentioned, the detectors are point detectors, so not camera-based. Like a camera, they are detecting photons and converting that to an electronic signal there. And then we apply an amplification to that signal, because obviously a single photon doesn't produce a lot of electrical signal. So we have to amplify that up using something called electronic gain. One of the downsides of this is if we increase the gain too much, then it's going to increase the noise of the detector as well. But fortunately, technology's come to a point where the detectors now are really pretty sensitive. So there are multiple different types of confocal detectors available. So On some of the older systems, you'll have a photomultiplier tube or a PMT. Some of the newer systems are a bit more sensitive, use things like gallium arsenide phosphide or gallium arsenide for longer wavelengths. The Leica systems now are using something called an avalanche photodiode, which is kind of a mixture of the two. And you'll see from the figures on the bottom here that different detectors have different sensitivities over given wavelengths. So this is the photomultiplier tube, the PMT. So this is using multi-alkali. So only about 30% sensitivity. If we go to GASP PMT, then that obviously increases but drops off quite dramatically at about 750. This is from Leica, so their high DS is up to 60% efficient in the kind of lower wavelengths, and then again that drops off. Or if you're really interested in the longer wavelengths, then they have a variety which is not as sensitive but is more sensitive in the far red ranges. And again, this comes from Zeiss. So this is their standard GASP detector, again drops off at about 750. And they've got a near infrared GASP and also a gas detector, which will push out now into the kind of 900 nanometer ranges, depending on the fluorophores that you want to detect. A lot of the detectors now can also undergo something called single photon counting. So they can essentially detect when a single photon hits your detector. And this is very useful for doing things like live cell imaging or in samples that are very faint or very prone to photobleaching. Okay, the last thing, as I mentioned, that we're scanning across our sample with the laser, and we're kind of binning the signal that comes back into individual pixels. So I guess, I mean, it probably applies the same to a camera, that although we're generating an image at the end of the day, it's essentially an array of intensity values. So say, for example, this small part of this image is actually just, could be an Excel spreadsheet with intensity values on it. So each pixel is coded for the intensity and also the wavelength of the photons that have been received. So that's something to bear in mind. We'll cover this on Thursday as well, in terms of, although it's generating an image, it's actually, essentially an Excel spreadsheet of numbers, so it becomes scientific data in that case. And one thing that we have to really be careful of with this is that when we're setting the number of pixels that we have in an image, that we're actually getting the resolution that we require to actually do our research. So there's examples here of different size pixels. You need to work out in advance what it is that you're actually trying to detect in the image. And again, we'll cover this on Thursday in terms of there's a bit of mathematics in terms of where your pixel sizes should be in terms of what you're trying to resolve within an image.